Well, hi there. I hope you're doing well. I want to extend a very warm welcome to you for dropping into this lecture. This is Lecture 3, corresponding to Chapter 10 of the textbook Applied Statistics, Business and Management Research. My name is Professor Andrew Timming, and in this lecture, I'm going to be talking about how to interpret logistic regressions. So in Lecture 1, corresponding to Chapter 10, I gave you an introduction to logistic regression analysis and walked you through some of the key concepts involved in this statistical technique. So obviously, if you haven't listened to Lecture 1, you should probably go back and do that first before proceeding to this lecture. In Lecture 2, corresponding to Chapter 10, I gave you a bit of a refresher in terms of how to understand probabilities, odds, as well as logged odds. And I told you how logged odds can be helpful in terms of fitting the sigmoid distribution, the S-shaped distribution that we use to estimate logistic regression analyses. Finally, in this final lecture on logistic regression, I'm going to walk you through the various ways in which you can interpret the results of a logistic regression analysis. So I hope you enjoy this lecture, and let's jump in. Here, once again, you can see the textbook that we're using for this course. It's my textbook, not to say that I own it, but I wrote it. It's entitled Applied Statistics, Business and Management Research, and it was written for the non-mathematician to come to terms with applied statistics or applied data science. Hope you have enjoyed reading it thus far and hope you will continue to enjoy reading it. As I've said before in the previous couple lectures, it's a good idea that you take some time to read this chapter, to read chapter 10 before you proceed with this lecture. But assuming that you have already read the chapter, then buckle up because we're going to get into some serious material on how to interpret a logistic regression analysis. Let's do it. You will remember that in multiple regression analysis, essentially what we're doing is we're looking at the impact on y for every 1 unit increase of x. So as our x variables move from lower to higher, how does that impact values of y, of our outcome or our dependent variable? In logistic regression, we have a very similar mechanism at play. So what we want to know in the context of logistic regression analysis is for every 1 unit increase in x, what is the effect of the probability of y happening or y not happening? So what is the probability given x of y taking place? Now, let's start with the logic of a simple binary regression model. If we build a simple logistic regression model or an equation, and this equation has one x variable, and that x variable is binary, that is to say nominal or categorical. And by definition, logistic regression has one binary y variable, that is to say categorical y variable. Then really what you have is a statistical test that looks a lot like a chi-square test, which we learned about previously. Remember, chi-square is a statistical method that we use when we want to look at whether two categorical variables are related to each other. And in this example of a simple logistic regression equation with one binary x and one binary y, that's exactly what we're doing. We're looking at how two binary or categorical variables are related to each other. But what's interesting about chi-squares is that it can only deal with categorical variables, right? It can't deal with ordinal variables with lots of categories, and it certainly can't deal with scale level predictors. On the other hand, logistic regression analyses can cope with dummy variables as well as ordinal variables as well as scale level predictors. Now, you'll also recall that multiple regression uses unstandardized B coefficients as well as standardized beta coefficients to explain or describe the relationship between X and Y. In the context of logistic regression, we don't use unstandardized B's or standardized betas. Instead, we use odds and logged odds as the key coefficients for describing the relationship between individual X variables and the Y yes or no, either or outcome variable. Think back to the previous lecture where I walked you through the concept of probabilities and odds. And I showed you how to start with a probability and convert that probability into odds. And then I also showed you how to convert odds into logged odds or logits. And the reason we convert odds into logged odds or logits is that odds can only have positive numbers, whereas logged odds or logits can have negative numbers as well as positive numbers, and that those numbers fit that S-shaped distribution, the sigmoid distribution. And you'll recall in the context of that discussion that positive numbers have a greater than 50% chance of happening, positive logits, and negative logits have a less than 50% chance of happening. So let's think about this just as an example. If we do an analysis looking at the odds of men being promoted next year, all right? And let's say that we find a logged odds of men being promoted next year are 1.98 compared to women. Now that's not the same as odds, right? Those are logged odds, not odds. And that does not mean, if you find a logged odds of 1.98, that does not mean that men are almost twice as likely to be promoted as women. That's not how you would interpret it, because it's hard to interpret logged odds. So what we need to do in order to interpret the results is to take those logged odds and convert them back into odds again, because odds are interpretable. They're intuitive, whereas logged odds are not. So to convert logged odds back into odds again, we use a process called exponentiation. So we carry out our analysis, our logistic regression analysis, using logits or using logged odds. But when we come to the interpretation of the analysis of our logistic regression, we don't want to try and interpret logged odds because they don't make a lot of intuitive sense for us. So what we need to do is to create what are called exponentiated odds. And fortunately, statistical software that we'll be using will do all this for you. You don't actually have to do the exponentiation yourself. So when we exponentiate logged odds and we create exponentiated odds, these can be read or interpreted in much the same way as normal odds, right? So just to give you a few examples here. If the exponentiated odds that you find are 1, then an exponentiated odds of 1 corresponds to an odds ratio of 1 to 1. And we know that an odds ratio of 1 to 1 means that there is essentially a 50% chance of something happening. And if there's a 50% chance of something happening given a particular input, given a particular independent variable, then essentially what we're going to conclude is that there's no effect, absolutely no effect of X on the probability of Y happening or not. So if you're, in other words, if your exponentiated odds for a given independent variable correspond to the value of 1, then your p-value is going to also correspond to greater than 0.999, because essentially it means that there is no effect of x on the probability of y happening or y not happening. If, however, the exponentiated odds are 2, if they come out as 2, then the way you would interpret this is that for every 1 unit increase in that particular x, then the odds of y happening go up by a factor of 2, or twice as likely, twice as much. So this would be the way in which you would interpret odds. Similarly, if you find odds that are less than 1, then that means that the probability of y happening is less than 50%, that the odds actually go down if you find a value of less than 1. Now, think back to some of the other statistical methods that you've learned throughout this course. Think back to, for example, the t-test. You remember that the t-test ultimately culminates in a t-statistic. And it's the t-statistic that will give you the p-value that will in turn tell you whether or not your results are generalizable. And think back to the ANOVA, right? The analysis of variance. The culmination of an analysis of variance is not a t-statistic, but an f-statistic. And your f-statistic will also correspond to a p-value that will tell you whether or not your ANOVA results can be generalized from the sample to the population. And you also learned when dealing with multiple regression that you use a t-statistic in the context of that multiple regression to determine statistical significance for each individual predictor vis-a-vis the dependent variable. In the context of logistic regression, which is the statistical technique that we're currently looking at, you don't use a t-statistic, you don't use an f-statistic. Instead, you use something called a walled statistic. So this is when you do a logistic regression calculation, the calculation results in a walled statistic. So the t-statistic and the f-statistic are based on a normal distribution. They're parametric tests. Logistic regression, on the other hand, when it creates a walled statistic, it doesn't use a t-distribution or a normal distribution. Instead, it uses a chi-square distribution, which we learned about in a previous chapter where we looked at the chi-square test. And the way we would interpret a walled statistic is that the larger the walled statistic, so as the walled statistic gets larger as a value, associated with a particular relationship between x and y, the more likely that the p-value associated with that relationship is less than 0.05. And you'll recall that a p-value that's less than 0.05 suggests that the result that we found within our sample can be reasonably confidently generalized to the wider population. Thinking back again to the chapter on multiple regression analysis, you will remember the concept of the coefficient of determination, also referred to as R squared, big R or capital R squared. And the way in which we use R squared is as an estimate of the overall goodness of fit of the model of the multiple regression model. And the way we interpret R squared is to say that an R squared value, when turned into a percentage, describes the amount of variation in our dependent variable that is explained by the sum of all our independent variables, or all our predictors together. And so the larger the R squared value, the better overall fit we have in our multiple regression model. So the larger the value, the better, because it means we have a better fitting model. Now, the problem is that we don't have R square at our disposal in the context of logistic regression. And the reason we don't have R squared at our disposal is that R squared, again, is a statistic that is based on parametric statistical tests, right? So we can't think about percentages of variation explained in the dependent variable when our dependent variable only has two categories, right? Remember, that's what a logistic regression is characterized by, an outcome that only has two categories. And with only two categories, we can't easily explain the amount of variation, right? But what we do have in logistic regression is something referred to as a pseudo R squared. Pseudo meaning kind of a fake R squared. It somewhat mimics the R squared that you would find in multiple regression, but you can't interpret it in the same way. So like an R squared in multiple regression, a pseudo R squared similarly is a number that falls between 0 and 1. And the way we would interpret it is that lower values, that is to say values that are closer to 0, represent a poorer fitting logistic regression model, whereas higher numbers, that is to say numbers that are closer to 1, indicate a better fitting logistic regression model. Okay, let's stop for a few moments and just reflect on some of the key points that you've learned about logistic regression analysis. In other words, what are the key points that you can take away from chapter 10 of the textbook? The first point I want to highlight is that logistic regression is a versatile statistical technique. It's a highly versatile technique, but it does have one limitation, and that's that you can only use it when you have a dichotomous outcome variable. That is to say, when your dependent variable has only two categories. That is to say, is a two-category nominal variable. It is, of course, capable of handling multiple independent variables simultaneously, just like multiple regression. The independent variables in logistic regression can be scale level. It copes very well with scale level variables. They can be ordinal, and they can also be nominal, but only two category nominal variables. In other words, dummy variables. Just like with multiple regression, if you have a predictor that is nominal with three or more categories, then you won't be able to use that as is in a logistic regression equation. You would have to convert it into a series of derivative dummy variables. Whereas multiple regression is based on the principle of ordinary least squares and the line of best fit, logistic regression is based on the concept of maximum likelihood estimation, or MLE. And it's this mechanism that enables prediction of the likelihood that Y will happen or will not happen. Obviously, as you've learned, logistic regression is predicated on the concept of probabilities and odds and logged odds and exponentiated odds. There are a lot of different ways you can express these types of results. Logged odds are used to calculate the effects because they fit nicely onto the sigmoid distribution, the S-shaped distribution. But logged odds in and of themselves aren't very intuitive, so we need to exponentiate those logged odds back into normal odds in order to clearly interpret the results of a logistic regression. And lastly, goodness of fit in logistic regression is assessed using something called a pseudo R squared, which can't be interpreted in the same way as the coefficient of determination in multiple regression, but it is a similar statistic. It's between a number between 0 and 1, where the higher the number corresponds to a better fitting overall model. At this stage, I would ask you to pause this video and either individually or in groups go through and answer the 6 questions that you can see in front of you. They will help you better understand the material that has been presented to you over the last 3 lectures. And thank you very much. Thanks for lending me your time, which I know is precious. I hope you have learned a thing or two about logistic regression analysis, and I look forward to seeing you at chapter 11. Bye now.